welcome to the 38th Surface Ventures keynote webinar. It'd be great for you to say hi in the chat and tell us where you're joining from today. I see we've already got a couple of people, Robert from Frankfurt and Daniel from Frome. Great to see you there. University of Leeds as well, fantastic. Thank you all for joining. My name is Dr. Sam McMaster. I am the content manager here at Surface Ventures. We are a non-for-profit organization, and our mission is to provide world-class surface and materials science education for academia and industry. Today, it is my pleasure to introduce Professor Ian Taylor from the University of Central Lancashire. After a degree in physics and a PhD in applied physics and electronics, Ian worked for Plessey Research from 1988 to 1991, and then joined Shell in 1991. He worked mainly in tribology and lubrication research whilst at Shell, and was Global Technology Manager for Shell's Lubrication Science team from 2006 to 2012. His research focused on energy-efficient lubricants, and he also managed Shell's University Research Wings in tribology from the mid-90s to 2020, working closely with various UK, US, and Chinese universities. His tribology research has resulted in over 70 papers in peer-reviewed scientific journals. Ian has been a visiting professor at the University of Central Lancashire since 2020 and is also a fellow of the Institute of Physics and of STLE. He received the Tribology Silver Medal from the Institution of Mechanical Engineers in 2020. Let's welcome Ian to the stage now. Whilst he's coming on stage, I'd just like to thank today's partner, Micromaterials. We'll have a short presentation from Professor Ben Beek later in the event. We'll also be releasing some poll questions and handouts from Micromaterials throughout. As we go along, please type your questions into the chat, and they will be marked for the Q&A session. We're planning to go for around 60 minutes today, and we'll be sharing a link for your attendance certificates later in the event. So without further ado, welcome Robert, or welcome Ian, apologies. And let me get your slides up and you can begin.
Okay.
There you go.
Thanks very much for the introduction, Sam.
Sorry, I noticed there's your audio doesn't appear to be working. Could you please refresh your browser window? We'll just check that that works. We begin. Okay.
Can you hear me now?
Oh, okay, so your audio was working.
Can you hear me?
Okay, so it looks like this might just be from my end, so I'll refresh my browser in a minute, but for now, please go ahead, take it away.
Okay, well, thank you very much, Sam, and thanks to Surface Ventures for inviting me to give this talk. So today I'm going to give a talk for about 30-35 minutes, talking about the economic and environmental importance of mixed and boundary lubrication. So an outline of the talk, I'm going to emphasize that initially that surfaces are rough rather than smooth, and that this leads to the idea that metal-to-metal contact and mixed and boundary lubrication can become important when the film thicknesses are too thin. I'll explain why mixed and boundary lubrication is becoming more important, and then I'll talk about how mixed and boundary lubrication can be measured in the laboratory and how it can also be measured in real machines. And then I will talk about how much does mixed boundary lubrication actually cost, and where do the costs come from. And in addition to that, I'll also talk about how much CO2 emissions are associated with mixed and boundary lubrication. And then I'll talk briefly about how we can reduce mixed and boundary lubrication in the future. So, I mean, this is basic tribology, so hopefully many of you on the call will be familiar with this. But at the micron scale, surfaces are rough. So if we have a parabolic slider moving against a flat surface as shown below, in fact, if we scale the vertical axis by about a factor of 1,000, we will see that the surfaces aren't smooth. So the centerline average of the parabolic slider is shown by the dashed black curve. But in fact, the actual surface will oscillate around that centerline average. And depending on how the component has been manufactured, there will be a probability distribution function associated with that roughness. And you can define a surface a root mean square roughness of the surface, which we call sigma 1 here, and similarly for the flat surface there's a sigma 2. And if we compare the film thickness to the square root of sigma 1 squared plus sigma 2 squared, we can define something called the lambda ratio, which effectively tells you how far apart the rough surfaces are separated. And you need a lambda value of about 3 or more to completely separate the rough surfaces. And if the lambda value is less than that, then you will start getting the rough surfaces interfering with each other and touching each other, and you'll get wear and friction occurring. So what this means is if we measure the friction coefficient, it will depend to a great extent on how thick the film is between the moving surfaces. And so the figure below in this slide shows what happens as we change the lambda ratio when two surfaces are sliding against each other. So when lambda is less than 1, effectively none of the load is carried by the fluid. All of the load is carried by the rough surfaces, and you end up with a friction coefficient which tends to be a fixed value of about between 0.1 and 0.2 typically. Then as the lambda ratio increases, as we increase the film thickness, we'll start getting some of the load carried by the fluid and some by the asperities. And so because some of the load is carried by the fluid, the friction coefficient drops from its value in the boundary regime, and it will drop and drop until the amount carried by the fluid is 100% and there's none carried by the asperities. So on the right hand side of this figure, the fluid is thick enough to completely separate the rough surfaces, and the friction is entirely determined by the properties of the fluid, things like viscosity. If we carry on increasing the value of lambda, we make the film thicker and thicker, the friction actually goes up because you've got to overcome all the friction of carrying this big thick fluid film. Now, in terms of predicting friction in machines, we know pretty well how to predict friction in fluid film components like bearings, for example. But what happens is it's more difficult to predict how much friction there is when you have a mixture of fluid film, lubrication, and metal-to-metal contact. So there's a lot of research going on in tribology to try and better understand how to describe what's going on in the mixed and boundary friction regimes. And one reason why mixed and boundary lubrication is becoming more important is because there's an increase in interest in making machines more efficient. And one way of doing that is to use lower viscosity lubricants. So this table below shows how the viscosity of passenger car lubricants has changed since about 1990. So if we go to 1990, a lot of people were using SAE 15W40 grades in their engines, and these had the viscosities as shown in the table. So about 114 centistokes at 40 degrees C, or about 15 centistokes at 100 degrees C, and a high temperature, high shear viscosity, which is measured at 150 degrees C and a shear rate of 10 to the 6 of about 3.5. So that was the situation in 1990. If we go to the present day, a lot of people are using 0W20 grade lubricants in their cars nowadays, and the viscosity has effectively halved at 40 degrees centigrade, has come down by about a third at 100 degrees centigrade, and has come down substantially at the high temperature, high shear viscosity. So the reason why the people have been using lower viscosity lubricants is because engines are primarily lubricated hydrodynamically. So if we reduce the viscosity of the fluid, we should reduce the friction in the engine and improve the fuel consumption. And that indeed is the case. But one of the ways in which the friction is reduced is by having a thinner film. And so there's more chance of mixed and boundary friction occurring, particularly at high loads and low speeds and stop-start conditions. So how can we measure mixed and boundary friction in the laboratory? So we typically use tribometers of various types. And an example shown here is a mini traction machine. which is effectively like a pin on disc machine, but instead of a pin, it uses a ball, and the ball can rotate or be fixed to slide. And this machine is filled with oil, and we're measuring the friction between the ball and the disc. And the reason this machine is quite a lot of interest in this machine is that the disc speed can vary from just a few millimeters per second to a few thousand millimeters per second. So the wide range of disc speed that can be used in this machine means that you can go from boundary friction right through mixed friction almost to hydrodynamic, depending on the temperature of the oil. And what we can do is we change the ball and the disc for each test. The disc and ball are usually quite smooth. The surface roughness is about a few nanometers, 5 nanometers for these for the typical samples used here. And we can simply test different lubricants to see what the effect of changing the lubricant is on the friction coefficient. And so we've got some results, typical results are shown here for a 10W40 engine lubricant. So this lubricant is the blue line in this graph. This particular lubricant will have quite a lot of anti-wear additive in, and that tends to give you quite a high friction coefficient of about 0.12, and it stays high up until about 100 or 200 millimeters per second. Then we see it dropping off as we go into the mixed lubrication regime. The grey line on this graph is a base oil. So this is a simple fluid with a certain viscosity and no lubricant additives in whatsoever. And then the red line shows a 0W20 formulated engine lubricant, and this time it has both an anti-wear additive in and a friction modifier. This would be a molybdenum based friction modifier. So we can see that in this particular instance, by changing the viscosity grade and putting a friction modifier in, we can go from a friction coefficient of 0.12 down to 0.04 at the lowest speeds. So this simply shows you that changing the lubricant can have a massive effect on the friction that we've got in these lubrication regimes. One thing that is worth commenting on, though, is that it's important to consider how to present the results from these machines. So on the left-hand side, we've got the results as then usually shown on a logarithmic scale. And this, to someone who's not familiar with this type of work, you get the impression that the boundary friction regime is really, really important, because almost half this graph you'll see in the boundary friction between a speed of about 5 millimeters per second up to about 100. And then the mixed regime doesn't seem quite as important because it's squished on this graph because of the nonlinear logarithmic scale that we used. If we plot the same data on a linear graph, we actually see that this boundary friction bit is a much smaller proportion of the test than you get than it would seem that if you plot it on a logarithmic scale. And for most machines, the proportion of time that you're in the boundary lubrication regime will be less than 1% typically, and you're more likely to be in the mixed regime than the boundary regime. So as tribologists, we do need to consider how results are presented and what perception those results give you by looking at the different ways they're presented. So although it's useful to plot on a logarithmic scale because you can get the wide speed range on that scale, it does sometimes give you the impression boundary friction is much more important than it actually is. Now, the mini traction machine has also been used recently by the Imperial College tribology group, and they did some interesting experiments where they tested a wide range of lubricants in the mini traction machine, and they subtracted the fluid film friction, and they normalized the data so that the boundary friction was normalized to 1, and crucially, they plotted the data not against speed, as is usually done in the mini traction machine, but they plotted against the lambda ratio. And they actually found that you could actually find a common curve for a lot of the lubricants that were tested. I should say none of these lubricants had friction modifiers in, but this work actually suggested that you could come up with fairly simple equations to predict the proportion of mixed and boundary friction, which in this case we called X, as a function of the lambda ratio with fairly simple equations. And in fact, some work I did with co-workers at the University of Central Lancashire, we actually compared this fit to commonly used mixed and boundary friction models, things such as the Greenwood Tripp model. And we actually found that the Greenwood and Tripp model under-predicted the mixed and boundary friction proportion compared to the experimental data from Imperial College and this curve fit. So this is all measuring mixed and boundary friction in the lab. What about in real machines? So this is some data from passenger car engines. So for passenger cars, there's lots of groups around the world that have directly measured the friction loss of engines. And typical data is shown on the left-hand curve, where this is a motored test. So the engine is not firing as it usually does. You're simply running the engine via an electric motor and measuring the friction loss of the bearings and the piston and the valve train. And what you tend to find is the friction goes up with engine speed, and for speeds greater than about 1500 RPM, the friction simply goes up with speed. And when friction goes up with speed, that's usually an indication you're in the hydrodynamic or fluid film lubrication regime. But if the speed is less than about 1000 RPM in this particular case, we see the friction starts to go up again at low speeds. And this is an example where you've got mixed and boundary friction. And in fact, in the reference quoted here, the friction of this engine was split between fluid film components and the mixed and boundary components. And we can see that mixed and boundary friction actually becomes greater than fluid film friction for speeds less than about 1200 RPM. So that was with a fairly old 1990s 2-litre gasoline engine, and it was a fully warmed up engine. The sump temperature was about 93 degrees centigrade. So we can see a considerable amount of mixed and boundary friction at low speed in this engine. And we also tested a different engine, and which was a 3-cylinder 0.66 litre engine. This is the type of engine used in these Japanese K cars, which are quite fuel efficient. And in this particular case, the engine was fired as well as it was fired as it's normally done in a real engine. And we found that, again, the friction mean effective pressure generally goes up with engine speed, but at very low speeds, we can see it go up at low speeds and go up as the speed decreases. So again, we see this effect that we see in mixed and boundary friction being quite important at low engine speeds. And this particular data also showed that, somewhat surprisingly, the friction in the engine was not it wasn't massively dependent on the load of the engine. As there's a slight effect, but it's not as big as you might imagine, which is one reason why motor tests are often done, because they don't usually give a substantially different friction than when you do it fired. Now, I should say that this simple graph on the left hides the fact that each component really has its own Strybeck curve. So this is the same data it's plotted again on the right-hand side, but we've plotted it in terms of the different component contributions. So the blue line shows how the valve train friction varies with speed, and it just keeps on going down with speed. So over the whole speed range of this test, the valve train is in the mixed and boundary friction regime, whereas we can contrast that with the red line, which is the journal bearings, and in that case the friction is simply going up with speed over the whole range, which suggests that the bearings are completely in the hydrodynamic fluid film regime for this test. And then you've got the piston assembly, which is the green line, and that's predominantly in fluid film lubrication for speeds above about 1000 RPM, but at the lower speeds we're seeing some mixed and boundary friction there as well. And then the timing chain is a bit complicated, but it's a fairly small contributor to this engine friction. The other thing about real machines is that there is a process called running in, which is quite important for friction. So when you've got two brand new components the rough surfaces, when they first touch, the highest asperities will tend to contact first. They will plastically deform, and you'll get wear occurring. And over the next 10 or hundreds of hours, the surfaces will actually modify themselves, and you'll usually find that the surface roughness of the new component is reduced after running in occurs, and that the friction of the new machine or new engine will be higher than when it's fully run in. And this graph shows some data from a paper from 1996, where they directly measured the friction force in a piston assembly for a brand new piston ring and a run-in piston ring. And we can see that for the new piston ring, there are quite large spikes occurring when the piston speed is 0 for the new ring. But once it's run in, there's substantially less mixed and boundary friction because of the lower surface roughness. And also the component can actually change shape. This occurs for piston rings. The shape can change, and that can subtly alter the film thickness in the piston ring and actually give you thicker films. So you can end up with the a worn ring giving you thicker films and having lower roughness, so that you can get a double effect on the lambda ratio. And so for a new piston ring, you could get the lambda ratio being maybe 1, but after it's running, it could be 3 or 4. So you can move from mixed and boundary through to fluid film. So that's showing what happens in real machines. Now, what about the costs of mixed and boundary friction? So there are really 3 components to how much mixed and boundary friction will cost someone. First of all, you've got friction occurring, and you have to supply fuel or energy to overcome that friction. And so the part of the cost is simply the energy used, the price you pay for the fuel that is used to overcome mixed and boundary friction. Secondly, mixed and boundary friction can cause wear, and so you can end up with parts wearing out and needing replacement. So you'll have to take the part out and put a new one in, and you've got the cost of to make the new part and to get it to where it's needed and fitting it. And then thirdly, in some situations in factories, you could get a key machine failing, and then the whole factory has to close down, and you're still paying workers, and there are lots of costs associated with unexpected breakdowns. So that's the main areas where costs occur. Now, in terms of passenger cars, under fuel economy tests, a lot of work has gone to try and work out how much fuel is used to overcome engine friction. And typically, because the fuel economy tests are done under low load, you need roughly 20% of the fuel that's used in the vehicle is used to overcome engine friction. And if you look at the data I presented earlier, you can actually look at the breakdown of engine friction in terms of its fluid film bit and its mixed and boundary bit, and you can actually come up with an estimate that about 5% of total fuel used is used to overcome mixed and boundary friction. So as a rough rule of thumb, for passenger cars, 20% of friction is used to overcome engine friction, and 3/4 of that is due to fluid film friction, and about 1/4 is due to mixed and boundary friction. And in a typical car that's used in the UK, typically people will use 1,000 litres of fuel a year. So if 5% of that fuel is used to overcome mixed and boundary friction, that's about 50 litres of fuel per year per car. So in the UK, there's about 30 million passenger cars, so we can multiply these numbers up, and we end up with quite large figures. So just for the UK, there's about 1.5 billion litres of fuel is used to overcome mixed and boundary friction, and that costs, each litre of fuel is about £1.50 a litre. And in addition, the cost of making the fuel, the CO2 emissions associated with burning the fuel and making the fuel, it's about 3 kilograms of CO2 emitted for each litre of fuel burnt. So we can sort of work out the numbers for the UK, and then we can extrapolate to the worldwide car population, which is so in the UK there's 30 million cars, worldwide there's about a billion cars. So if we multiply these numbers up worldwide, about 50 billion litres of fuel are used to overcome mixed and boundary friction at a cost of about $100 billion, with CO2 emissions of about 155 million tonnes. So these are large figures. Now, another area we could look at is heavy-duty trucks. Now, somewhat counterintuitively, heavy-duty trucks engines are much more hydrodynamic than small gasoline engines. So on the left-hand side, we've got the graph I showed earlier, showing how the friction varies with engine speed for a typical 2-litre gasoline engine. In the right-hand graph, I've replotted data from a 2012 paper from Ricardo and Infinium, where they measure the friction of a large diesel engine. So this would probably be about a 10-litre capacity diesel engine. And what we see is the friction of that engine just goes up with engine speed, and there's no indication that there's a turn up in friction at low speeds. And this is because as you scale an engine up from, say, a small 1-litre gasoline engine to a 10-litre diesel engine, the scaling up of that engine, the hydrodynamic parts become more important compared to the valve train, which is mainly the mixed and the component which has most mixed and boundary friction. And in addition, if you scale the valve train up, it actually becomes easier to lubricate. And in addition, when you've got a larger engine, you've got space to put rolling elements into the valve train, whereas in a small gasoline engine, it's usually sliding elements in the valve train. So what happens in a large diesel engine is it's much more hydrodynamic than a small gasoline engine. And at the same time, heavy-duty diesel engines are used in trucks which are quite heavily loaded. So when you have a heavily loaded vehicle, the proportion of friction, the proportion of fuel used to overcome friction decreases. So you've got two effects happening in a heavy-duty truck. You've got less fuel needed to overcome friction. So whereas in a gasoline engine, we said 20% of fuel was needed to overcome engine friction, in a heavy-duty truck, it's more like 10% of the fuel is used to overcome friction. And in addition, the amount of mixed and boundary friction in the heavy-duty engine is lower, so we could use an average figure of 10% for the proportion of mixed boundary friction in the heavy-duty engine. So in the gasoline engine, we had a figure of 20% for the fuel used to overcome engine friction, and the average amount of mixed and boundary friction was about 20–25%, whereas these figures have come down in the heavy-duty truck. So when you multiply these two figures together, you end up with a figure that 1% of fuel used in a heavy-duty truck is used to overcome mixed and boundary friction, whereas we came up with a figure of 5% for passenger car engines. So although only 1% of fuel is only needed to overcome mixed and boundary friction in a heavy-duty truck, this is counterbalanced by the fact that the fuel consumption of heavy-duty trucks is much, much larger than passenger cars. So you've got two effects going on for a heavy-duty truck. First of all, the fuel consumption of the truck is a lot larger. It's about 30 litres per 100 kilometres compared to 6 or 7 for a passenger car. And secondly, the annual mileage of a truck is a lot larger, about 10 times larger than that of a car. So for a typical truck, the annual fuel consumption is about 30,000 litres of fuel compared to 1,000 litres for passenger cars. So when we combine all these figures, we end up with a figure that roughly 300 litres of fuel per year is used to overcome mixed and boundary friction at a cost of about £450 and CO2 emissions of almost 1,000 kilograms. And again, worldwide, there are about 300 million heavy-duty trucks. So when you do the sums, you actually find that the figure for a heavy-duty truck for overcoming mixed and boundary friction in terms of both amounts of fuel used and finance and CO2 emissions, they're actually higher than the numbers coming from passenger cars, even though the amount of mixed and boundary friction is actually lower in the heavy-duty truck. So we've seen that there are some very large numbers here on how much fuel is used to overcome mixed and boundary friction, what that means financially, and how much CO2 emissions there are. So there's a lot of interest in the tribology community to how to reduce mixed and boundary friction. And there are really three main approaches. First of all, we could try and reduce the friction coefficient between the moving surfaces. So we can use friction modifier additives in lubricants. We could look at using alternative materials, such as ceramics and DLC. And there's a lot of research going on in tribology labs looking at super lubricity. Can we make changes to the surfaces so that you almost get a order of magnitude reduction in friction coefficient by making the surfaces super lubricious? The second thing you can do is you can try and alter the surface roughness profile. So you could actually super finish components and reduce the surface roughness, but this obviously adds expense to the finished component. The other thing that you could do is you could put deliberate surface texturing onto components to increase the load-bearing capacity of the surfaces and actually increase the film thickness. And the third thing you could do is you could actually try and reduce the operating conditions where mixed and boundary friction dominates. So, for example, in cars and trucks, you will get most mixed and boundary friction occurring when the engine idles. So if you have a stop-start system in those vehicles where the engine stops when the vehicle is stationary, you effectively remove those operating conditions, and you will obviously reduce the amount of mixed and boundary friction. And the other thing you could do is you could reduce lubricant temperatures as well, and that will increase the viscosity of the fluid and increase the film thickness. So I've just about finished, hopefully just about on time. Hopefully I've convinced you that mixed and boundary friction is becoming more important because lubricant viscosity is going down. In addition, power densities of machines are going up. Lubricant temperatures tend to be increasing and sump volumes are decreasing. We've done some detailed calculations for passenger cars and trucks and found that for passenger cars, about 5% of the total fuel used in a passenger car and 1% of the total fuel used in a heavy-duty truck are used to overcome mixed and boundary friction. And these costs, just the energy costs, I've not talked about the cost due to wear or replacement parts, simply the energy costs amount to enormous figures to overcome mixed and boundary friction. So for passenger cars and heavy-duty trucks, we've estimated about 150 billion litres of fuel are used to overcome mixed and boundary friction at a cost approaching $300 billion. CO2 emissions of almost 500 million tonnes. And so these are very, very large figures, and it focuses the mind of the tribology community that the need to reduce mixed and boundary friction, as well as being good in terms of reducing friction and making machines more energy efficient, it will have a massive impact on the amount of fuel used, cost to the customer, and CO2 emissions. And research on reducing mixed and boundary friction, including topics such as super lubricity, are going to be very important in the future for both customers and the environment. So thank you for listening, and I'm happy to answer any questions, which I think will be after Ben's talk. So thank you very much.
Thank you very much, Ian, for that fantastic talk. So, as you said, let's now invite Ben on stage. So he will be giving us a short presentation from Micromaterials. Hello, Ben.
Hi, Sam.
Let me just get your slides up. There you go. And there you go. Take it away.
Okay, thanks very much. Well, a hard act to follow there from Ian. That was fascinating. So, in the poll questions, there was we asked how many in the audience were interested in reducing abrasion in their materials they're studying. So, hopefully, this little segment from me will be quite interesting. So, we've developed a new test technique for our nanotest system to simulate the abrasive contact more effectively than having just random repetitive scratches in the same place. So what we're doing here is we're controlling, putting scratches on a surface with controlled distribution, and that allows us to simulate abrasion more accurately. So, as I said, the tests are carried out within our Nanotest Vantage, which is a multifunctional nanomechanical test platform. So it has the capability to do indentation, scratch, wear, impact, reciprocating tests, things like that, at nano and micro scales, also in different environments, in hot and cold, and in different liquids or different humidities. And we can combine our Tribo testing capability with multi-sensing through monitoring things like the acoustic emission or contact resistance, as well as we measure obviously the friction and the depth in the tests. So you've just heard about how we want to minimize friction in sliding elements, and we want to minimize friction through abrasive wear. So abrasive contacts, these are just pulled off the internet essentially. So clearly they cause surface damage. Clearly it's one of the most common general wear mechanisms, if not the most common general wear mechanism. And so what we've done with our nano scratch test is we've modified that or added some additional capability to allow us to produce these multi-pass scratch tests, where between each pass we move the position with a sort of semi-random but a computer-generated statistical distribution of start points. And these distributions can be normal around a surface position, or they can be so-called rectangular distributions where there's equal probability of any starting anywhere. And we can change these region widths, and we can change the loads, and we can change the number of scratches. So why this is important essentially is, John Williams showed years and years ago essentially, is that if you're scratching something and it's a perfectly smooth sample, then you typically you're going to get ploughing or something like that. But when you've got some surface roughness, then you get transition to more severe wear modes like cutting and abrasion. So what's happening here is that the damage from one scratch, or the pile up even from one scratch, is affecting the next scratch nearby, and this is leading to transitions in mechanism. So here's just a very simple example. In this case, this is for optical coatings that were produced so on a transparent substrate, essentially, when there was a problem in the coating deposition where the plasma pre-cleaning wasn't working effectively. And in this case, you can see clearly that there's a big adhesion problem, and the random scratch test, or the statistically distributed scratch test, has picked that up quite nicely there. So you're getting complete removal of these areas in the test, which is a much more effective way of doing this than a standard nano scratch test. So here's another example, in this case for a nuclear application, a collaboration with the University of Huddersfield. And here what we're seeing essentially is two different high entropy alloy coatings that are very sort of mechanically similar, and they're being tested here under the same conditions. But what you can see is that the one on the left is much more brittle than the one on the right. So the one on the right is clearly a much more abrasively resistant coating. So that's all pictures of the surface, but actually what we can do is we can track the deformations cycle by cycle within the test. And this, we can track the deformation along the entire track. We can look at mean values on those tracks, and we can then look and see how those mean values change as a function of cycles. In this case, is an example where after about 20 cycles, this surface is essentially quite resistant to failure, but then after somewhere around 20-25 cycles, then you're getting a transition to a more abrupt damage regime, essentially. So this is just the depth, but of course you've got the friction or whatever other signals you've got at the same time. So the correlation between those signals is very useful, because it allows you then to look at, for example, transitions between even third body abrasive wear situations, and you can see where you're getting that transient rolling contacts as well as pure sliding contacts. So this is the sort of thing that you might get under relatively light conditions. So here's an example on just a silicon wafer, so quite light load, and you're getting a little bit of brittle damage. Those dark spots that are there, but essentially it's quite a sort of fairly well behaved surface. If you run that test on or do it in more severe conditions, in this case it's higher load, more passes, and here you can see transitions in certain areas to much more extreme damage modes. There's a lot more of this brittle debris, and you're even getting, in this case, lateral cracking in the silicon. So that's quite a severe test. We have recently published on this, on these high entropy alloys. So there's a paper here, and this is just out now. So it's free to download in that journal there. So you're welcome to search for that. And there's just some pretty pictures essentially from that paper. One of the things I didn't show is these angled plots as well, which just illustrate where the damage is occurring, and you know exactly which is which, so you can track how what causes the transitions to more severe mechanisms. So we can also look at metallic materials, so this as well as these sort of hard coatings. So these are, excuse me, just an example where we have titanium grade 9 essentially, and here we're just doing these randomized scratch tests. This is 50 scratches in these 3 tests, but all that's happening is we're changing the region width. So in the bottom one, all the scratches are in the same position. Above it, they're slightly close together, and then above it still we're getting they're a bit wider apart. And you can straight away see all of this brittle damage around the edges where you're getting these brittle machining out of material. And if we look on contrast, under pretty similar conditions, in this case on a more ductile material, here we're getting essentially a much cleaner response, and you're just starting maybe to get that transition towards these ductile chipping under the same conditions. So this is quite a useful way to test the abrasion resistance of new materials you're developing. Okay, so hopefully that was of interest. So I showed some data, all of which at room temperature. We're downstairs in the lab at the moment. We're doing similar tests for a project sponsored by the UK Space Agency, and in that test we're doing high temperature abrasion tests as well. And it's really starting to help our fundamental understanding of the mechanisms in abrasive wear now. And so we think we have a unique tool to design more damage tolerant materials. It's equally applicable to coatings and bulk materials, and it exists in the current version of the nanotest scratch module. Okay, thanks very much. Back to Sam if he's coming back.
Yes.
There he goes. Yeah.
There you go. Thank you very much. It was a great presentation. It was nice seeing new features for the nanotest platform. So before we begin our Q&A, let's invite Ian back on stage. Just take those slides off, and let me make the attendance certificate available for everyone. So there we go. So please do go ahead and click that. The link will be active for the next day, so you can download your attendance certificate. But don't leave just yet. We'll still got a few questions to answer, and yeah, let's proceed. Let's proceed with that. So we have our first question, and I think you did put some comments in the chat, but if we can go ahead and answer some of those now. Our first question, excuse me, from Rizwan, who asks, did they measure friction for each component separately on separate test rigs and then combine them in the graph shown? Or did they use a single test rig and separate the friction results through some other means?
Yeah, so I have answered this in the text, but basically they measured the friction of the total engine in a motored situation where they're basically running the crankshaft with a motor, and then they measure the friction of the total engine, and then they do it again after they've taken, say, the valve train off, and the friction will be lower, and the difference is taken to be the valve train friction, and then they take the pistons out, by doing this, they can sort of get at the total friction of the engine, but also the component bits. I mean, it's not quite as simple as I mentioned. I mean, the full detail is given in the reference on that slide in the talk, you have to put weights on to counteract the fact you take the pistons out to make the forces on the journal bearings correct. But all of that was done by a company in the UK called Ricardo, who are used to doing these things. So it was a motored friction test, but it's known as a friction teardown test. And so you can get access to the total friction of the engine. And lots of people do motored friction measurements on engines, and you get that sort of total friction curve, which sort of goes up with speed and then goes up again with speed at low speeds, showing the mixed and boundary friction. But there's not that many, there's not that much data in the literature where people have done the teardown test to get at the individual components. So hopefully that helps. There's more details in the paper, as I mentioned.
Okay, thank you. Move on to our next question from Xavier, who I think you may have also answered a little bit of, but it says, in the piston ring friction force measurement after running in, I would still expect larger friction forces at the top and bottom dead centers, i.e. when the speeds approach zero, than at half stroke, i.e. higher speeds. How is that?
Well, it depends on the operating conditions. It depends on the RPM, and it also depends on the lubricant and the temperature. I mean, if you have a fairly thick lubricant and low temperatures, you can definitely get the friction at mid-stroke being higher than that at the dead centers. So, I mean, I'd have to look at the original paper to see what the operating conditions were. And also, you can put a friction modifier in your lubricant. You can reduce the spikes at the dead center positions compared to a lubricant without friction modifiers in. So it really depends on the operating conditions and the lubricant formulation. But if you're at high temperatures, the engine's fully warmed up, and you've got a thin oil, you're probably correct. The friction at the dead centers will probably be greater than that at mid-stroke. But one thing that is worth pointing out is that what's important for fuel consumption is not friction, but power. And so this is again a situation where what you present is important. I presented, and that data was taken from a paper where they measured the friction force. If you actually plotted the power, that dead center positions, the speed is zero. And so that you drastically decrease the weighting of the mixed and boundary friction around dead centers because the speed is very low, and you increase the weighting of the bit in the middle. So in fact, that's one reason why, although mixed and boundary friction are important in a piston assembly, particularly for wear, they don't really make much contribution to the overall fuel consumption because the speeds are low around dead center positions. And in the engine, as I presented in the slides, most of the mixed and boundary friction in engines is coming from the valve train. And the amount coming from the pistons is less than you might imagine from when you see graphs of friction versus crank angle.
Thanks, Ian. We have another quite a far-reaching question here from Castria, who asks, what is the realistic future of engine oils?
Yeah, that's a good question. I mean, for anyone on the call who's in the lubricants business, I mean, I wouldn't worry for about 20 years, to be honest, because even though countries are talking about banning the sale of conventional cars from 2030 or 2035, cars generally have a lifetime of 15 years. So if you bought a brand new petrol engine in the UK in the end of 2029, I mean, it's going to last until the mid 40s. And you've got to realize that the world is very large. So although the number of cars in, say, Europe and the US is probably saturated or even declining, the number of vehicles in Asia, India, China are increasing quite dramatically. So I think the International Energy Agency is expecting the number of combustion engines to go up between now and 2040 or 2050 quite substantially. Plus, you're also going to have hybrid cars. So it's not clear to me if there is a ban on conventional cars, certainly, but you're also going to have cars coming on which have got hybrid cars, got both an engine and battery. So you're still going to have engine oils in those. The more interesting question really is what the impact is on innovation, because when people, if there's a ban on conventional cars coming in, people aren't going to make new engines, and if they don't make new engines, there's not going to be a need for new engine oil specifications. So you're almost going to freeze the lubricant formulations at a certain point in time, because there's not going to be a need for any new lubricant specifications, and that's going to potentially put a brake on additive innovations, because a lot of the funds for making new additives is coming from the automotive sector. So you could end up with a much bigger impact on the tribology community, because rather than this ever-ending cycle of developing new lubricants because new specs are coming in, once people stop developing new engines, you're always going to freeze the lubricant at a certain point in time, and there's not going to be a need for new formulations or new additives in certain regions of the world.
Yeah, that's very insightful. And so there was, I think Castro did write another question that I think you have pretty much answered. You said, for me, the future of engine oils is directly related to the future of hybrid cars, since internal combustion engines being restricted. Do you agree? I think
well, yeah, I mean, I would say that is one area where specs could change, because at the moment there's no specifications for hybrid car engine lubricants. The people who make these cars simply use a standard engine oil, and so that's one area where you could end up with some specifications coming in specifically for hybrid engines.
Yes, that's quite interesting as well. So let's continue with our questions. We got one for Ben here from Giusy, I think at Leeds, who says, "Thank you, Ben. What's the substrate used for testing? And how does the substrate hardness affect the whole wear test results?"
Well, yes, certainly it will come into it. So in all of these tribological situations with thin coatings, then the load is not being fully supported by the coating. So particularly in the tests on silicon, silicon undergoes phase transformations and some sort of lateral dominated cracking, essentially at fairly high contact pressures in around sort of 10 gigapascals. But often it can be the substrate failure that might happen first, or it can be that the coating failure or interfacial failure happens, and then you're no longer then protecting the substrate. So you can get multi-stage failures, particularly, I didn't show any of that, but on thin sort of PVD nitride based coatings, that sort of thing can be quite dramatic, and it's all down, a large portion is down to substrate failure. So obviously less help, but they have often less load support, so it's a compromise depending on the application.
That element of coating design is always quite tricky, trying to balance properties between coating and substrate. Just a quick comment on the question that asks, can we get a copy of the slides? Fortunately, the slides themselves will not be available, but for all of you that have registered, you will get a replay of this, from which you will be able to see the slides again, but we will not be sending out the slides themselves directly. Okay, continuing with our questions from Daniel, who asks, Ian, how does this general approach map across other machinery types, such as gears, compressors, hydraulics, turbines?
Well, that's something we're working on at the moment. So we've tried to estimate how much energy is used to overcome mixed and boundary friction in passenger cars and heavy duty trucks. We're trying to look at things like gears, rolling element bearings, and trying to get some representative numbers for those sectors as well. I mean, what was instructive to me was that in heavy-duty trucks, the amount of energy used to overcome mixed and boundary friction is a factor of 5 times lower than that in cars for a particular vehicle. But because of the massive amount of fuel used by these trucks, the overall impact is actually greater. So you could have something like a rolling element bearing where the power loss is actually quite small, but if you've got a certain proportion of the time is mixed and boundary friction, because there's 50 billion odd bearings in the world, that could actually be quite substantial. It's not as easy though to get typical operating conditions for some of these other machines. So although there's data around for gears, things in industrial applications, they don't usually have standard driving cycles, and there's not usually as much data around as to how they're operated and how much is fluid film and how much is boundary. But we are trying to extend this study to look at a wider range of machines to get a sort of better overall sort of view of this.
Okay, thanks, Ian. Let's move on to our next question from Omar. I hope I'm pronouncing that correctly. Who asks, what about lubricant usage regime in electric vehicles? May it be fuel cells, hybrid, or battery powered? What are the tribological challenges in electric vehicles too?
Well, if it's a full battery vehicle, it's not got an engine, so you'd have to focus on things like the gearbox and the bearings in the motors. So those anything that moves is likely to have some element of mixed and boundary friction, particularly at stop-start. And in a hybrid engine, in a hybrid vehicle, you do have an engine, and in fact, there's probably going to be a lot more stop-start. So you could well have mixed and boundary friction associated with stop-start, but on the other hand, in a hybrid engine, because the engine is not on all the time, the average lube temperature is lower. So there are like conflicting things going on in a hybrid engine, and it's you'd have to do a sort of complete sort of study of the engine really and its operating conditions to try and work out what the impact is.
Okay, thanks, Ian. Got a question from Trevor here who asks, Ian, I'm sure most people would perceive engine idling as being low load. To them, it's counterintuitive to say that engine idling is a high load situation. Can you elaborate, please? Also, how does stop-start introduce shock loads? Sorry.
Yeah, sorry if I gave the wrong impression. Mixed lubrication in general tends to increase when you've got low speeds and high loads, but it's not like it's an either or thing. So at engine idle, you're right, it is low load, but it's the low speed which is giving you mixed and boundary friction. If you've got low loads and high, if you've got low speeds and high loads, you'll get even more. But it's the low speed which is giving you the mixed and boundary friction in idling, as opposed to the load. And in terms of the stop-start introducing shock loads, it's the algorithm for when stop-start occurs is quite complicated. When you first start your car, it's got to warm up a bit before the stop-start comes in. And so the components will already be lubricated. And then when it stops, it's only usually stopped for a few seconds before it starts again. So it's not like a proper stop-start from cold. Generally, there is an increased load on the bearing that's closest to the starter motor. And some OEMs make that bearing bigger. So there can be design changes to the engine to cope with the stop-start. But I'm not aware of a lot of issues in the field associated with stop-start, because there's a lot of engines out there in Europe have been using stop-start for the last 5 to 10 years, and I think the engineering is to cope with that is pretty well advanced.
Okay, thank you. We have another question from Suresh. I hope I'm pronouncing that correctly. Are there any emerging technologies or materials that show promise in reducing friction and improving the overall performance of valve trains? What a question.
Yeah, well, I mean, I think there's increasing use of ceramics and diamond-like carbon coatings in valve trains. So often the tappet is made of DLC now. and that's as much to address wear issues as it is to address friction. The problem with gasoline cars is that the engines tend to be quite small, so that you can't really put rolling elements in. Ideally, you'd want to have a rolling element in there rather than a sliding element. But because the engines are so small, there's not enough room to do that. Whereas in heavy-duty diesel engines, they tend to have rolling elements in, which will typically reduce the valve train friction by a factor of 2. So if you could somehow get a rolling element into a small gasoline engine, that would help. I think
Sam's clearly having problems with his. So do you want to, Ian, just, if you look at the chat and, Sam's back.
Oh, yeah, apologies for that. I muted myself to clear my throat. Unfortunately, my audio to go. Apologies for that. Yeah, sorry. Thank you. I did catch most of that answer. Thank you very much. I think we
yeah, the super lubricity, that's an interesting one. I think that's definitely a technology that is at the research stage, and a lot of the tribology research, it's basically in vacuum or in dry contact. I mean, I think if they could adapt the learnings on super lubricity to a liquid lubricated contact, I mean, that could have some real applications, but how far that is off, I'm not sure. But typically friction coefficients are probably 0.1 to 0.2 for most applications. If you add a friction modifier into the lubricant, like a molybdenum based one, you can get that down to maybe 0.05, but there's only really passenger car lubricants that use friction modifiers at the moment. The friction modifier additives aren't used in heavy duty diesel engine lubricants, and they're not usually used in industrial lubricants. So that's one way of reducing friction, but it's a fairly expensive way of doing it. But if you can actually make the components out of materials which inherently have a lower friction coefficient, that would be a better solution, I think. But how far off the research that's going on in the tribology labs on super lubricity is from commercialization, I'm not sure at the moment.
Yeah. I know there has been some work, I remember from Leeds, on embedding graphene nanoplatelets into DLC coatings that could achieve ultra low friction. Similarly, I think some of Diana Berman, some of her work on, I think it was like effectively like nano scroll carbonaceous films with DLC. Yeah, so it's still, very innovative work, but as you say, and quite far off any kind of actual adaptation.
Yeah.
Yes. Yeah. Got one final question there from Sid, who asks I guess addressed to me, which is what are the best possible solutions for reducing friction to increase super lubricity? I'm going to put that question to Ian and Ben. What do you think on this?
Yeah, I mean, I think I'm not an expert in this area at all. I think the thing is that you can get things working in the lab in sort of nice environments, but quite a lot of work is needed to get it working in a real environment at an economically attractive price. I mean, you've got to, it's not just a case of something working; it's got to be economically, workable as well. So when people make machines, it's a pretty cutthroat business in terms of pricing for parts and components, and often a lot of the problems with gearboxes is they're often made too rough because it's too expensive to finish them to a sort of a smoother finish. So it's not just a case of whether you get something working in the lab in an ideal environment, it's whether you can actually translate that to a real environment and actually get the price down so it's attractive. So I think there's quite a lot of work done before that research starts getting rolled out and working in real applications.
Yeah, I'm not sure it's true, but I've even heard something similar. But for medical implant materials, that they could improve the performance by spending time on the surface finishing, but it's not considered productive to do it. So
yeah, I think just for that amount of machining time, for the small amount of surface roughness change you get, and also just the amount of effort in, I guess, actually programming that, or whatever method it is you want to use that, be it electropolishing, it's it's difficult to scale up to a lot of parts. So yeah,
Okay.
I guess on the increasing super lubricity is keep an eye on research papers, and I guess we can revisit that question in a few years and see if anyone's been able to innovate something that's actually scalable. But yes. Okay, so I think with that we've addressed all the questions. Thank you very much, Ian and Ben, for going through all of those in such detail. And let's now wrap up the webinar. So with that, I'd like to say thank you very much to Ben and to Micromaterials for supporting this event. We wouldn't be able to do what we do without our partners. Thank you very much, Ian, for the fascinating talk. Fantastic, fantastic points brought up, and great audience engagement and questions there. So thank you very much. So we like to say to everyone who's here, please do visit our website. You can see some of the other things that we do. You can view our recordings of our previous events. You can see our newsletter, the next edition of which is releasing tomorrow, and sign up to our mailing list in order to receive that. You can also now register for our next keynote on the 25th of April with Professor Ashley Martini. And finally, I'd like to say, please do take the time to advertise these lectures to your contacts. It'd be great for us to continue growing our audience and having more of you join these webinars. So with that, thank you both very much, and thank you everyone for joining.
Thanks. Bye.
Thanks, and thanks again to Sam as well for excellent hosting as usual.
Yes.
Thanks.
Always a pleasure. All right. Thanks, Ian. Thanks, Ben.
Thanks. Bye-bye.